So now this video discusses about what we call it as the quantum numbers. What are the quantum numbers and how should you be able to understand about the quantum numbers and their principles behind? So this video discusses all those things. Just have to pay attention and stay focused. We understand that we have three subatomic particles. We have what we call them as the electrons, and we have what we call them as the protons, and I also have what we call as the neutrons. So these are said to be the subatomic particles, and basically according to the principles behind the atomic structure, and this is how these active particles are allocated. And basically atomic structure is composed of the nucleus, which is the center, and it is composed of the energy levels. We also call them as the active shells. In the nucleus contains the protons as well as the neutrons, and outside the nucleus contains the rings-like structure known as, we call them as the energy levels, or we call them as the shells. So in the shells, that's where the electrons are found. And the allocation of these electrons follows what we call as, now the configuration of these electrons follows the principle of the configuration using the active KLMN notation, which states that the maximum number of electrons should be the maximum number of electrons in which a particular energy level must have to occupy, must be given as 2n squared, where n corresponds to the energy level. And for instance, energy level, let's say energy level 1, we call it as n is equal to 1, and the maximum number of electrons has to be given as 2 times 1 to the power 2, that is given as 2. So which means in energy level number 1 there must be 2 electrons. And how about in the energy level number 2? In the energy level number 2 we should have it as 2 times 2 to the power 2, that is given as 8 electrons. It means in the energy level number 2 the maximum number of electrons must be given as should be 8. And how about the energy level number 3? So we'll have it as should be 3 to the power 2, that is given as should be 18. So it means in the actual energy level number 3 we must have 18 electrons, and so forth. So that's how you start to understand about the configuration using KLMN notation, and which is to say in the first energy level must have 2 electrons, in the second 8, 18, we have 32, that is fourth energy level, we have it as 32, and 15th energy level we have it as 64, and we can have it going up to that way. That is what we call as the configuration using KLMN notation. But now, according to the principles behind the quantum numbers, in actually each and every energy level contains what we call them as subshells. And in those subshells contains what we call them as orbitals. And by the way, we have the energy level, and inside the energy level we also have what we call them as sub-energy levels, or we call them as the subshells. And inside the subshells, that's where the electrons are located. Now the quantum numbers, much of it discusses about the quantum numbers, much of it tries to allocate where the electrons are located in a given energy level. So if we say a quantum numbers, this is the set of the numbers that it describes about the allocation position in the energy level in which the electrons are found. That's how you have to understand it. So this is the set of the numbers that it describes the a position in the energy level as well as the orientation in which a particular electron in the energy level should be in an atom basically located. That is what we call as the quantum numbers. We'll be able to allocate in which actual energy level does the certain electron is located, in which orbital, in which the subshell, or in which the orientation is the certain orbital actually is, in which the certain actual electron is located. That is what we call as the quantum numbers. And we have 4 sets of the quantum numbers. We have what we call as the principal quantum numbers. We have what we call as the principal quantum numbers. So what is the principal quantum numbers? So principal quantum numbers, these numbers describes about the energy level. They describe about the energy level of an electron. Describes about the energy level of the electrons. Should be the energy level of the electrons. That is what we call as the principal quantum numbers. It describes about the energy levels of the electrons. And by the way, the energy levels are denoted as, should be n. That starts from 1, 2, 3 up to somewhere. So energy levels starts from 1, 2 up to somewhere. That is what we call as the principal quantum numbers. And basically these energy levels increases with the increase of the atomic number. No wonder, let's say, if we think of energy levels or the subshells for calcium are not the same as that of the oxygen. A calcium has more energy levels than oxygen because they have different atomic number. So energy levels increases with actually atomic number. So energy level, actually principal quantum numbers, describes about the energy level in which the electron is located. And mind you, our interest is to just have to allocate the certain electron in an atom. So if we are to allocate an electron in an atom, we should have to identify what is its energy level in which that particular atom, in which actually that particular electron is actually located. So that's what we call it as the principal quantum number. And apart from the principal quantum number, we also have what we call it as the azimuthal quantum number. We have what we call it as the azimuthal quantum number, or we call it as the angular quantum number. So what is azimuthal quantum number, or that is angular quantum number? Now the point of interest is that in a given energy level, let's say we have that one. In a given energy level, there contains what we call them as subshells, and inside the subshells contains what we call them as should be the orbitals. Now, azimuthal quantum number describes about the shapes of those actually subshells and also the shapes of the orbitals. That's what we call as the azimuthal quantum numbers. And it states that, in a given actual energy level contains the subshells that are denoted as S, P, G, F, let's say G, H. So in a given actually energy level contains the subshells given as S, P, D, F, G, H. And now the shapes of actually these subshells, they are actually described by the azimuthal quantum number, or the angular actually quantum numbers. So should be that. And basically AC subshell, it is said to be the spherical shape. So it has a spherical shape, that is S subshell, and P subshell is said to be having a peanut shape. So it is said to be having a peanut shape. And how about D subshell? And the D subshell is said to be having, should be double peanut. It's said to be having the double peanut. That is the shape of the D subshell. And that of should be F orbital is said to be having the flower shape. It's said to be having the flower shape. So that's how you start to understand about the shapes of the suborbitals. And how can you be able to determine these the values corresponding to the L values corresponding to these suborbitals? how should we be able to determine the actual error values corresponding to these suborbitals? So determining the error values, determining the error values corresponding to, corresponding to, subshells, and basically given the principal quantum number given us that. How should we have it? Let's say if we have the principal quantum number given as 1, and the formula for actually azimuthal quantum number, it is given as L is equal to n minus 1, and which is equal to 0. And the possible values of the subshells ranges from negative L to positive L. So the possible values of the subshells ranges from negative L to positive L. And now since we have the only single value of L, which is negative, it means the only possible value is 0. And that corresponds to have it as for actually a subshell AC. And since this is the subshell AC from the energy level 1, then we'll have it as, should be given as 1S. 1 corresponds to the principal quantum number, and the AC corresponds to the subshell that is actually a subshell that is in the energy level 1. So which means in all cases, in the first shell, there contains only actually a subshell S. That's how you should have understand it. But according to the principles behind, any subshell S must have 2 electrons. So in a subshell S must have 2 electrons. We'll talk about this in due course in the same video as well. But just have to understand that in the actual energy level 1, there contains only 1 subshell, and which is specifically S subshell, actually S subshell. How about in energy level 2? Now in energy level 2, we have the azimuthal quantum number given as 2 minus 1, and which is given as should be 1. In the possible values of the actually subshells, we'll have it as should be, and let me take it back. You should have to understand that. Let me take it back here, and I have to classify something. I've confused something here. And by the way, the possible values of the subshells, ranges from 0 to the power actually to the value of L. That is the possible values of the subshells ranges from 0 to the particular value of L. And now for this case, we only have the single value of L, which is 0. It means the possible values is just 0, and that corresponds to have it as 1S. Since it is just that 0, it means it is 1S. So 1 corresponds to the principal quantum number, and in the subshell S must have maximum of 2 electrons, so which means we'll have 2 electrons. And also in the same case, you have to understand that in the first energy level must have only 2, actually must have only AC subshell. Just have that. And sorry for confusing you there, but just have to understand it in that way. Let's say in the second energy level. Now in the second energy level, the value of the subshell should be an azimuthal quantum number is given as 2 minus 1, which is equal to 1. And the possible values of the subshells will have from 0 to 1. And 0 corresponds to S, and that is 2S, since it is the subshell from the energy level 2. And the other one is said to be P. We'll have it as 2P, since it is a subshell from the energy level number 2. And in all cases, in the actually P subshell must have the maximum number of electrons given as 6, and that is according to the standard. So which means in the S subshell must have 2 electrons, and the P subshell must have 6 electrons. If we sum up these electrons, it will give us the 8 electrons, which is in line with the configuration using KLM notation. That states that in the second energy level must have 8 electrons. So in this case, it means in the second energy level must have only 2 subshells, that is S as well as the B. And in the S subshell must have 2 electrons, and the P subshell must have 6 electrons, adding up to 8 electrons in line with the actual configuration using a KLM notation. And how about in the actually third energy level? Third energy level, we have the value of L, which is given as 3 minus 1. And the possible value of the subshell ranges from 1 should be 0, 1, 2 to 3. And by the way, should be just that. So in the actually 30 energy level, we must have we have the value of L, which is given as 2, and the possible values of the subshells ranges from 0 to 2, so which means we have 0, 1, 2, and the first one corresponds to have it as 3s, and of which s has to be 2 electrons, and I will have 3p6, and I'll have 3 actually AD. It should be in D, we should have 10 electrons. So in the third energy level, we have 3 subshells, S, P, as well as the D. And as it stands here, it means that 3 corresponds to the energy level in which the S subshell belongs, and also in this case remains the same. Now, as you can see, if you sum up the electrons, we have the 18 electrons in line with the principle behind the configuration using KLM notation, where in the third energy level must have 18 electrons. So in the third energy level, we only have 3 subshells, as you can see there. So that's how we can determine the subshells if we are being given, the principal quantum number. And let's say if we have the energy should be a quantum number, should be a principal quantum number given as 4. If that is the case, L will be given as 3, and the possible values of the actual subshells will have 0, 1, 2, 3, and that corresponds to have it as 4s. 4s2 should be 4p6, of course, we can have that, and 4d should be 10, and the other one is 4f, of which f must have 14 electrons according to the standard. So if you sum up these electrons, you see that in the fourth energy level must have 32 electrons as of their standard, as you can see it here. So which means in the fourth energy level must have 4 4 subshells, as you can see it there. So this is now how you should have it. Wherever if you have, let's say, 2p, that means it corresponds that this is the subshell P from the energy level 2. If you have, let's say, 5f, it means this is a subshell actually f from the energy level actually 5. If you have, let's say, actually a 2s, it means this is the subshell s from the energy level 2. So that's the information you can get from the actually subshells. And now another actually a quantum number is so now another quantum number we call it as the magnetic quantum number. We call it as the magnetic quantum number. Now this one expresses or describes about the orientation of the orbitals. So this one discuss about the orientation of orbitals, on a 3-dimension actually system. So it describes about the orientation of the orbitals on a three-dimension actual system. That is what they call as the magnetic quantum number, and it is symbolized as ML. And basically, it carries the value, ranges from negative L to positive L. From negative L to positive L. So which means, let's say if we have, if we have the azimuthal quantum number L given as 2, it means the values of the magnetic quantum numbers we have it as negative 2, negative 1, 0, 1, 2. And let's say if we have, let's say, L given as 1, it means the values of the ML will have it as negative 1, 0, positive 1. And that is, what if, let's say, if we have the MLs, let's say if we have the ML given as, let's say, 0, it means the possible values of the ML also be 0 as well. What if we have L's given as 3? It means the MLs will have negative 3, negative 2, negative 1, 0, 1, 2, 3. And how about the ML should be, if we have the L given as 4? So if L is given as 4, it means we'll have the ML, being given as the negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, up to 4. So that's how you start to understand that. And how should we have to determine, the values of the possible magnetic quantum numbers given the principal quantum number? Let's say we have the principal quantum number given as, let's say, 1. And now for this case, we have the L being given as should be 0. Now for this case, what is the possible values of what are the possible values of the subshells? We have the subshell ranges from 0 to L, which is the same as 0. For this case, it means we have subshell 1s. So it means in subshell 1s, what is the value of the L corresponding to subshell S? Subshell 1s, it is given as L is given as 0. So it means the value of the ML will have it as 0. And what if we have the subshell given as 2? The value of L is given as, it should be 1. And the possible values of the subshell, we have it as 0, 1. So that corresponds to have it as, should be 2s, and this is 2b, as you already know. And it means the value of L corresponding to 2s, it is given as 0, and of which the values of the ML will also be 0. And how about if we have a 2b? Now on the case of the 2b, the value of the L corresponding to actually 2b is given as 1. So it means the values of the ML will have it as the negative 1, 0, should be 1. So that's how you should have understand that. And also, if let's say if we have n is equal to 3, the value of L is given as 2, and the possible value of the subshells 1, 2 should be 0, 1, 2, and of which this is 3a's. That this is should be 3b. That should be, and that this corresponds to have it as 3b, and this corresponds to have it as 3d. So what is the value of L corresponding to 3s? We have it as 0, so which means ML will be given as 0. And how about the value of actually L corresponding to 3b? We have it as should be 1. It means the ML will have it as negative 1, 0, positive 1. And how about the value of L corresponding to 3d? We have it as 2, so which means the ML will have negative 2, negative 1, 0, 1, 2. So that's how you start to understand about determining the values of the ML, given the principal quantum number. Now, what is the information we can have from, let's say if we have, this case, we have, let's say, a 5D. How can we have the magnetic quantum number corresponding to 5D? Now, first thing, we should have to understand that a 5 corresponds to the principal quantum number given as that. And what is the L corresponding to the principal quantum number 5? We have it as a 4. In the possible values of the subshells, we have 0, 1, 2, 3, 4. And that corresponds to have it as, should be 4s, and 4p should be that of, should be this 5s rather. We should have it as a 5s. We have 5d, we have 5f, we have sb, s should be 5p rather. Here we should have 5p. We have 5p, 5d, 5f, and 5g. So our interest is on the 5d, and what is the value of L corresponding to d? We have it as 2. So which means ML corresponding to 5d will be given as negative 2, negative 1, 0, 1, 2. Should be that. And how about if we have a surge of, let's say, 3p? What is the value of the M? What are the values of the ML with respect to the 3p? So this is a subshell from the energy level should be 3, where n is given as 3. So we need to determine L corresponding to 3p, of which the L corresponding to n3 is given as 2. So have 0, 1, 2. And the 3p, belongs to this. So this is 3p. And what is its value of L? We have it as after 1, that is negative 1, 0, 1. So these are the possible values of the L. And also try to have this. What are the values of the ML corresponding to, of 5F, let's say 40, let's say 7, let's say 7p, and let's say 3s, and let's say we should have it as 2p. So try to have that on at your own time. But now, what is the information we can have from the summation of the MLs? So summation of the actually MLs gives us the total number of orbitals in a given energy level. And for instance, let's say if we have the energy level 3, and we have the value of L, which is given as 2, and the possible values of should be subshells. So we have 0, 1, as well as 2. And now from this case, you should have to understand that, this is 3s, this is, we have it as 3p, and we have, this is, this is 3d, sbd, that is okay. And now let's go for after the 3s. On a 3s should be 3s. 3s, the value of L corresponding to 3s is given as should be 0, of which ML corresponds to should be 0. And let's go for 3p, and the value of L corresponding to 3p is given as 1, of which ML is given as negative 1, 0, positive 1. And let's go for 3d. The value of L corresponding to 3d is given as 2. So which means we have ML given as negative 2, negative 1, 0, 1, 2. Now in a subshell, actually in energy level 3, or in the shell number 3, in a shell 3, have, I should start with the, let's say, in a subshell actually S3, there is only one orbital. That is one orbital. In other words, there is only a single room that actually accommodates 2 electrons in the actually 3s orbital. So why are we having one orbital actually? Because we only have single value of the ML. And in subshell B, we have 3 orbitals because we have 3 values of the ML. 1, 2, 3. It means there contains 3 rooms that accommodates 6 electrons in B subshell. And in a D subshell, there contains 5 orbitals. Should be 5 orbitals, 1, 2, 3, 4, 5, and that accommodates 10 electrons in a D subshell. And if you sum up this in a subshell, actually, if you sum up this in the energy level 3, we have about, should be 9 orbitals. We have about 9 orbitals. That is. And how about if we have, let's say, energy level 5? What did you say? So principle remains the same. We have the value of L, which is given as 4, and the values of the subshells corresponds to L4 is given as 0, 1, 2, 3, 4, and this is 5s. That is 5s, 5b, 5d, 5f, and this is I'll say 5g. Now the value of L corresponds to 5s is given as L. Therefore, for 5s, ML is given as L. That is 1 orbital. And let's go for 5b. The value of L corresponding to 5b is given as 1. Therefore, ML, ranges from -1 to +1. It means there are 3 orbitals. And in 5d, we have the L given as 2. Therefore, ML corresponds to -2, -1, 0, 1, 2. Corresponds to having 1, 2, 3, 4. It means there are 4 orbitals. And 5f, the value of L, it is given as 3. And that will correspond to have it as, -3, -2, -1, 0, 1, 2, 3. 1, 2, 3, 4, 5, 6. It means we have 6 orbitals. 6 orbitals. And likewise, you should also do the same with 5G. And you observe that at the end of the day, the total number of sub-orbitals, I should say, actually, total number of the orbitals in a given energy level, it is given as n to the power 5, actually n to the power 2. So that is the formula I can use to have the total number of orbitals in a given energy level. Simply, it is n to the power 2. And sorry for the interruption. In fact, my PC is running short of power. And now let's look at another actually. And by the way, try to verify the total number of total number of orbitals for the following. Let's say if we have n is equal to 2, you should have to verify if the total number of orbitals is really 4. You should have to verify if the total number of orbitals is really is 4. And also try if we have the n is equal to 4. We should have to verify if the total number of orbitals is given as really 16. And also we should have to verify if is, let's say, n is equal, should be 6, we should have to verify if the total number of should be orbitals is 36. So try to have that. And let's now look at the final, actually a quantum number, which is electron spin. Electron spin. And we are saying we have the principal quantum number that tells us about the energy level. And inside the energy level contains what we call them as the subshells. And now inside the subshells contains what we call them as the orbitals. And inside the orbitals, that's where the electrons are found. And now how are those electrons are oriented now is described by the electron spin. According to the principles behind the electron spin, let's say this is a typical orbital. And in an orbital, there must be the maximum number of electrons given as actually 2. And these electrons must point in the opposite spin, in the sense that the one must face up and the other one must face down. And now, why should they have to face in the opposite spin? Because if they face in the same spin, electrons are actually, these electrons are equally charged. Now, if they are to face in the same direction, there will be a force of repulsion. They won't be able to stay in the given orbital. But if they face in the opposite spin, it means there will be a force of attraction that will make them to stay in the particular orbital. So that's what we call as the electron spin. Now, the one that faces up carries the value of +5, and the one that faces down carries the value of the -5. This is what we call as the electron spin concept. And let's say we have subshell 2p. Determine the set of the 4 quantum numbers corresponding to subshell 2p. Now, first thing, we have the actually principal quantum number given as 2, and we need to have what is the value of L corresponding to the quantum number, principal quantum number 2. We have it as 1. But this actually, a value of L is not for 2p, because 2p is the subshell. So we need to have the value of L corresponding to 2p. And what is that L? We are going to have it from the set of the subshells from this L. Now, that case we have it as 0, 1. And where this is 2s and this is 2p. So which means the value of L corresponding to 2p is given as, should be 1. Is given as 1. And how about the values of the ML? ML will be given as -1, 0, +1. And how about the magnetic quantum number, which is symbolized as MS? We'll have it as a +5 or -5. So the set of the possible quantum numbers is given as any 2, L is given as 1, and the ML is given as the -1, 0, +1, and MS is given as the half or -half. That is. Now, how about, let's say, if we have, let's say a 4D. How should you have the set of the 4 quantum numbers with 4D? So n is given as 4 in that way. And what is the value of L corresponding to 4? Actually, we'll have it as 3. Then we should have the L corresponding to 4D. And how should you have that one? We have 0, 1, 2, 3. And this is corresponds to have it as, should be 4s, and that this is 4b, and this is 4d. So which means the L corresponding to 4d is given as 2. And how about the values of the ML? Have -2, -1, 0, 1, +2. And how about the MS? We'll have it as a +half or -half. That is. And I also try to have the following at your own time as well. Just have to determine the values of the four set of the quantum numbers and are corresponding to, let's say, 7s, 7d, let's say 5b, and that should be, let's say, 4b. And also try to have that as, let's say, 3s, and let's say should be 60. Try to have that. Now let's be talking about what they call as the order of subshells. Now the order subshells corresponds to have, starting from the lower energy level subshells to the upper energy level subshells. So here is the order you should have to understand, and to make sure you understand this actual order clearly. I'll just have to present it as we have it as 1s, and I must have 2 electrons, and we have 2s2, and in all cases, a subshell S must have 2 electrons. So you should have to understand this order. It should be 5s2, we should have 6s2, we should have 7s2, and then we have 2b6, and then we have, here we should have 3. By the way, then we should have 3s2, 3b6, and we should have 3d10, and I have 4s2, 4 actually b6, and we have 4d10, and also we have it as 4f14, and we have 5s2, and 5b6, 5d10, and 5f14. Mind you, in a subshell F must have 14 electrons. And we have 6s2, 6b6, and 6d10. Of course, we can also have 6f14 can be that, but let me just have to put it there. And we have 7s2, and we have 7b6. Let's just have that. And now the order of the actual subshells ranges like this. So this is how the order has to be. This is the order you just have to. And this is the order you just have to understand. And this is a subshell with the lowest energy level. We start from 1s2, and from 1s2, then we go out and enter again here, that is 2s2, and from 2s2 we enter again through there, we have 2b6, and from there we also go actually 2b6, then 3s2, and we go again, we enter again for should be 3b6, and from there 4s2, and we enter again, and we should go for 3d10, and 4b6, and we have 5s2, then we enter again having 4d10, 5b6, and 4s2, and we also enter again there in that one until we also go for that. So that is the order in which the subshells are arranged, and in all cases this is how the order has to be from what we have done it here. So the order starts from you know, the order has to lands like this. So the order starts from 1s2 and 2s2, and we have it as 2b6. We have 3s2, 3b6, and 4s2. We have 3d10, and we also have, should be 4b6, and after 4b6 we have 5s2, and after 5s2 we have it as 4d10, and after 4d10 we have 5b6, and from there we have 6s2, and we have it as 4l14, and I also have 5d10, and we have 6b6, and from there we have 7s2, we have 5f14. So that is the order, and we also have 6d10, and that is 7b6. So this order tries to tell us that, you know, this is the lowest energy level. Actually, this is the subshell with the lowest energy level, and this is the subshell from the highest energy level. That is, in this way we are increasing the energy level. So which means actually electrons cannot occupy 2s2 before 1s2, and likewise electrons cannot occupy 4d10 before they occupy 4s2, actually 5s2, because this is the subshell of the lower energy level than this. Electrons cannot occupy 5d10, should be 6d10 before they occupy this, and they can't occupy this before this. So that is how you start to understand that one. So make sure that you understand the order, and basically much of it you start to understand about that actually a diagram I presented about these subshells. That's a very important and the key thing to understand about. So now that we understood about you know, the arrangements of the subshells, as I'm saying, the subshells ranges from the, you know, a subshell with the lowest energy level and goes up. Now let's be able to understand about the allocations of the electrons. Allocations of electrons. How are the electrons allocated in the subshells, or specifically in the orbitals? Allocations of electrons. There are several principles behind the allocation of the electrons, and the first one is what we call as the Aufbau's principle. Now, Aufbau's principle, Aufbau's principle, you know, this principle states that the electron cannot occupy, you know, electrons occupies energy levels with the lowest energy level first. As I already talked about that, you know, electrons cannot occupy 2s2 before they occupy 1s2. So according to that order of the arrangements of the subshells, you can see that we had the likes of 1s2, that is the order, 1s2, 2s2, let's say 2b6, and let's say 3s2, just have to mention the few, and I also had the 3b6. Now according to the Aufbau's principle, electrons cannot occupy this subshell before they occupy this, and likewise they can't occupy this before they occupy this. Electrons occupies the subshell with lowest energy level first. So that is the principle behind the Aufbau, you should have to understand. And we also have another principle, which is the Pauli exclusion principle, and which states that, you know, if two electrons occupies the same orbital of the same energy level, they must have, you know, points in the opposite spins. Now the point of interest is this: let's say if we have the energy level given as 2. Now in the energy level given as 2, the possible values of the subshells in the energy level 2, we have 2s2, and we also have what we call it as 2p6. This you should have to understand. And you should have to understand that in a given orbital, there must be the maximum of 2 electrons in the given orbital. And for instance, orbital diagram for 2s2, it is given as that one. So according to the actually Pauli exclusion principle, should be Pauli's exclusion principle. It states that, let's say for instance, in 2s2 there are 2 electrons, and all these 2 electrons must occupy this orbital. Therefore, they must point in the opposite spin. They must have to actually point in the opposite spin. And in subshell P, there must be 3 actual orbitals to make sure that 2 orbitals are in each orbital. Actually, 2 electrons are in each orbital. So have that one. And according to the principle behind the Pauli exclusion principle, we should have these actually electrons points in the opposite spin. That's what it means. And we also have another principle, which is that of Hans law. According to the Hans law states that electrons occupies orbitals of the same energy level in a way that makes the number of electrons with the same actual spin that actually points should be electrons occupies the orbitals of the same energy level in a way that makes the number of electrons with the same spin direction as large as possible. In other words, let's say if we have the subshell, let's say subshell P, and we understand that the subshell must have 6 electrons, and it must have should be 3 orbitals rather. It must have 3 orbitals. But now whenever we are feeding the electrons in these actual orbitals, first thing we should have to fill the electrons points in the one direction first. Then we should have to fill the other in the opposite direction, like that. Don't fill the electrons like that, where you can have, don't fill the electrons like this. Don't do like this. It should be this, then have that, then this. No, don't do that. But you should have to fill the electrons in such that the electrons facing the same direction first. They should have to complete the move, then you should have to start with other ones in the other way direction. That's how you should have it. And why are we doing that? Because if we have the electrons, let's say if we do like this, let's say if we have this and this and this, what happens is that no electron can move from its orbital to another orbital because there will be a force of repulsion. But if we think of having, let's say, and for instance, let's say you cannot have to, let's say, do this like that, because the moment you have fulfilled this one and come for this, as you are coming for this one will jump to this, because they are facing the opposite direction. There will be the force of actual attraction. And if we have, let's say, P given as 4, Stromo, this is subshell P, and this is subshell P. Stromo, no matter what, it must have actually 3 orbitals, and that is you should have it. And now first thing, we should have to fill the electrons in the one spin, and the next we should have that one. So this is how it will be. And since we are having 4 electrons, if we have, let's say, P2, principle remains the same, we still more have 3 orbitals. We have that and that and that and that. So this is how it will be. If we have, let's say, P5, we can have it in the same way. have it as having 3 orbitals, or have it as that, then we'll come for the other one that will be given as that. So this is how it should have to be. And in subshell D, we understand there has to be 10 electrons, and that constitutes to having 5 orbitals. So we should have that, and we have that one according to the Hans law should be that, and I should have to come for the other ones like that. Let's say if we have D5, principle remains the same. We should have it as, we'll have it as being given as that. So this is how it will be. And even let's say if we have D6, it means we'll have another one here. If we had, let's say, D7, it means we can have something about there. So this is how should have, that is according to the Hans law. So keep that in mind. And now that we understood about a sort of the orbital diagrams and the arrangements of the arrangements of the subshells in terms of the increase in the energy levels, now we can be talking about what we call as the electron configuration using the orbital diagrams as well as the SPDF. So apart from the configuration using KLM notation, we can also be able to have the configuration using the SPDF as well as the orbital diagrams. And for instance, let's go for calcium. Calcium is having 20 electrons, and now using the order of the configuration, that is SPDF, you can have the configuration of the calcium being given as SPDF configuration will be given as, we'll have it as 1s2. Make sure you understand the order, 1s2, and that means we are remaining with should be 18 electrons, and we have 2s2. It means now we are remaining with 16 electrons, and we have 2p6. Now we are remaining with should be 10 electrons, and we have what we call as 3s2, should be 3s2. So in this case we have, these are 10 electrons, 12 from 20, it means we are remaining with 8 electrons, and from 3s2 we should have to go for 3p6. So it means we'll be remaining with 2 electrons, and from 3p6 we have 4s2. It means now that is the SPDF configuration of a calcium. Now using the orbital diagrams, it means I will have, for 1s2 we'll have 1s2 will have the electrons going like that, and corresponding to 2s2 we also have it in the same way going over like that. That is a 2s2, and we have 2p6. It means we should have 6 orbitals, which should be, we have 3 orbitals, and we should have to have it in that way, and we should have it in that way. Then I should go for, now that is 2p6, then we should have to go for 3s2. 3s2 must have 2 electrons like that, and we should have to go for 3p6. How about 3p6? 3p6 you have a 4 of them, so have it as that, and 4s2, now we are having 4 electrons there, that is 4s2. So that's how we actually do the configuration using SPDF as well as the orbital diagrams. And how about if we have, let's say, What if we have, let's say, chlorine, which is Cl? What is the configuration for chlorine if that is the case? Chlorine is 17, that we have 1s2, and by the way, try to have that at your own time, and also try to have the configuration and for the following. And I understand you can be able to have the configuration. You can be able to have the configuration. Let's say if we have the sodium, try to have the configuration using orbital diagrams as well as the actually SPDF, and also try to have the configuration for neon, and also configuration for nitrogen, and also the configuration for carbon. So try to have that configuration for carbon, and also try to have the configuration for gallium. Try to have the configuration for gallium, and also try to have the configuration for rubidium, and magnesium as well. Try to have the configuration. Titanium, try to have the configuration, and we also have the iron, try to have its configuration, and we have the nickel, we have a nickel, try to have its configuration using SPDF notation as well as the orbital diagrams. And let's say on the case of the carbon, a carbon is having 6 electrons. Now the actually configuration using the SPDF, we have 1s2, and we have 2s2, and we have 2p. Now in this case we have 2 electrons in subshell B. So the configuration using the orbital diagrams, you still have it in the same way. We have 1s2, that will go like that, and 4s2, that will go like that. And by the way, that is 4s2, should be 2s2, not 4. 2s2 will go like that. How about the 2p5? It should be 2p, should be 2. 2p2 principle remains the same. Since we are in the subshell B, we still have 3 orbitals, and despite that we have a few number of electrons, and we have that and as that. So this is 2p, is actually 2p2. That will be the way out. Now let's be talking about what we call as the ground state configuration, or the noble gas configuration that is incorporating the noble gases. Let's say if we have the calcium is having 20 electrons, and the configuration of the calcium, we said it is given as 1s2, and we also have 2s2, and we have 2p6, 3s2, and how many electrons are here? We have 10 electrons, and here we have, this is 12 electrons. Now we have the 12 electrons, and from actually 3s2 we have 3p6, and from there we have 4s2. This is the configuration for the calcium. But from the actually lowest energy level, actually lowest subshell, what is the actually a noble gas that we can incorporate with and in the configuration for the actually a calcium? We have the possible noble gases like helium having 2 electrons. We have neon having 10 electrons. We have argon having 18 electrons. Now the noble gas that we can use should be given as the argon. That is at least the one with the maximum number of electrons but less than 20. Instead of having neon, we'll have argon. So argon is where is the argon ending? Argon having 18 electrons, it is ending here. So in this case it means we have it has argon. Then what is remaining? We are remaining with 4s2. So this is what we call as the ground state configuration of the calcium. And all you need is to be well conversant with the periodic table and be able to identify the noble gases that you can use. And for the sake of interest, elements in group 2A, let's say barium, its noble gas configuration, it is given as, helium 2s2. That should be barium. And magnesium, its noble gas configuration, it is given as the neon, and we have 3s2. And we have the barium, and that is its noble gas configuration is given as that one, 6s2, like that. And we have radium, its noble gas configuration is Rn. So make sure you understand about the periodic table in terms of the actual elements, that's noble gases. And we have some other, let's say, elements like gallium, its noble gas configuration, we have it as argon. And we have 3d10 and 4s2 and 4p1. That should be that, of course. And we also have the likes of krypton and sort of. But that's how you should have to understand about the electron configuration that uses the noble gases. And for the sake of interest, let's say if we have, a chlorine and having 17 electrons, using KLMN notation, we have 2 electrons in the first shell, and we have 8 electrons in the second shell, and we'll have 7 electrons in the third shell, of course that is. But what is the SPDF configuration corresponding to the outermost shell electrons? And what is the SPDF notations configuration corresponding to the actually second energy level electrons? And let's say if we have, let's say, a calcium having 20 electrons, what is the actually SPDF configuration corresponding to the electrons in the third energy level? And also here is another task for you. And looking at the phosphorus, what is the configuration using SPDF corresponding to the electrons in the actually outermost energy level, which is the valence electrons? How about if we have also this one? I want to see the responses in the comment section if you are able to have that one. And also if we have, let's say, radium, what is the configuration SPDF corresponding to the electrons in the outermost energy level? Otherwise, that's how you start to understand that one. And also here is the task for you. Go and look for the actual exceptions on the configuration using SPDF. And this is just a task for you. Thank you.